Okay, today we will discuss about duct sizing selection. Okay, like how to
Mhm.
size the ducting based on different applications. Clear, right?
Understood. Yeah.
Okay. See now, if you go to ASHRAE, we have a duct design chapter 34. Okay, based on that,
Mm,
we are going to design it. Okay, the duct sizing.
mm,
Okay, if you
mm,
go to the system design methods, okay, you can
mm,
see there are
mm,
different methods. Okay, to design the ducting. One is equal friction method, and another one is static method. Okay, then there is a
mm,
T method, velocity reduction method. Okay, total pressure
mm,
method, constant velocity, residential system design method. Okay, there are different systems are there. Okay, now
mm.
if you talk about in this system, okay, most of the most system which is used for residential and commercial application is the equal friction method. Okay,
Okay. Mm, mm,
okay, and if you talk about the velocity reduction, it is nothing but you will reduce the velocity starting from equipment to the nearest airflow rate. Okay,
Yes.
to the nearest the discharge. Okay, like
Air outlet.
where
Yes.
you air outlet, you can say like that. Okay, so till
Yeah.
till the time you will start from increasing the velocity to reducing the velocity, so that is called reduction method. So when you talk about the velocity table, okay, if you go this is the maximum duct velocity table, right? You can see different applications, residence application,
Mhm,
theater, or average stores, different application is there. So you have a
mm.
main ducts, this is the velocity, right?
This is an FPM, if I'm not wrong,
This is the
right?
FPM, yes, FPM. Okay, this is the main ducts and this is the branch duct, and this is the
Mm,
duct to reach your the final velocity based on the noise generation. Okay, say for
mm.
example, I need a so and so residential project. You may require like a 29 dBA, 27 dBA,
Mm.
something like that, right? During night time.
Yeah.
Okay,
Yeah. Yeah.
so you will start from main ducting like 1000 FPM, and you will end up with 600 FPM for the supply.
Mm, mm, mm,
Okay, when you talk about return, you will start from 800 and you will end up with the 600 FPM. But this is not a final. You will do the acoustic study, so that will give you the final velocity. Clear,
yeah.
right? Okay,
Mhm,
so
mhm.
this is the based on, like, you cannot say like thumb rule, but this is the velocity based on the research, you can say, right?
Yeah. Yeah. Yeah.
Okay, so say for example, if it is
Mm,
a private office, you can go starting from 2000 to 1200 FPM. Okay, if you talk about average stores, you can start from 2000 FPM to 1800 FPM. Okay,
mm,
so this is
mm,
the velocity table basically.
mm, mm, mm,
Okay, say for example, this is one of the project where you can see the duct sizing. Okay, you can see that air distribution sizing. Starting from the main
yeah.
duct, you can go up to 7 meter per second. This is based on this particular table only. Okay, and the branch
Yes.
duct, you can go 5 meter per second.
Mm.
Okay, then the louver, sun trap louver, this is everything based on ASHRAE. If you go to ASHRAE
That's right.
duct design chapter, what will be the optimum velocity? So this is basically based on the research, based on the different previous experience. Only the velocity is defined. Okay, it is
Mm,
like you cannot say like thumb rule, but you can say it is based on the research, right?
mm, mm, mm,
Okay,
mm.
now if you talk
Understood.
about
Understood.
fan coil unit, the nominal velocity, okay, or the based on the equal friction method, the best pressure drop will be 0.5 pascal per meter. Okay, you can take a range like zero point 0.4 to zero point 0.6 pascal per meter.
Mm,
Okay,
mm,
but
mm, mm.
approximately for the fan coil unit, for if you go with any fan coil unit, approximately you will go with the zero point 0.5 pascal per meter. Okay, so there are different factors. It is not only say for example duct sizing method. Okay, you have to talk about throw, you have to talk about noise control. Okay,
Mm,
then you have to talk about the equipment designing. Say for example, if you go with the zero point 0.5 pascal per meter, okay, you may end
mm.
up with the total static pressure will be like a 20 pascal or 30 pascal, right?
Yes, yes,
Okay,
yes.
but if you go with the FCU manufacturer, you may ask for the model, right? FCU manufacturer
Yes,
will be
yes.
having a model, right? Say for
Model.
example,
Yes.
this is a model 1, this is a model
Mm,
2. Okay, you,
mm.
you might have seen different models, right? So if you
Yes,
talk about
yes.
this model, starting from the static pressure, will some of the manufacturer will be starting from 30 pascal, then 50 pascal, then 75 pascal, then 100
100%. Yeah.
pascal, 150 pascal,
Mm,
something like that. Okay,
mm,
so the
mm,
way you
mm, mm.
increase the pascal, it will affect your power consumption, right?
Yes. The
Okay,
higher the
so
Pascal, higher the electrical power that we require.
electrical power consumption. Okay, now the
Yes, yes.
optimum velocity for the residential, say for example, this is your room. Okay, and you're keeping
Mm-hmm.
your FCU here, and you're going to keep the ducting like this, right? And
Yeah.
what is the pressure drop you have to maintain per meter? That is for the FCU, it is 0.5 pascal per meter, so
Point
that
5 Pascal.
you can throw it with the effective throw and also with less reduction noise. less velocity, whatever the required velocity, okay, and the required duct sizing. So these are all the optimum based on different research, you can say like that. So for if you talk about any of the fan coil unit, it will be for 0.5 Pascal per meter. Okay.
Yes.
Okay. And if you talk about AHUs, like you have a general ventilation fans or AHU, okay, or a fresh air handling unit, you may talk about like 0.6 Pascal per meter. So you can have a range 0.5 Pascal per meter to 0.7 Pascal per meter, right?
Yeah.
So this is the range to size the ducting. Okay. If you talk about like kitchen parking application, smoke extract duct, okay, or some other applications where you can go up to 0.9 Pascal per meter. Okay, so the range can be 0.8 Pascal per meter to 1 Pascal per meter. Clear, right?
Understood. Yes.
Okay, so this is the duct design criteria. Okay, you can say design criteria, right? Okay, when you go to the duct design chapter as per ASHRAE, okay, you heard about static pressure and velocity pressure, right?
Static pressure, yes, but velocity pressure, I'm not really sure.
Okay, let me tell you one small example. You may have you can understand. See, this is the ducting, right? Okay.
Yes.
Say for example, you have a fan, right? There is a pressure. There is a pressure acting on the ducting, right?
Yes.
When your fan runs, okay, assume that when the fan is rotating, okay. So what will happen? There is a pressure inside, okay. The pressure will be acting on the duct surface, right?
Yes.
That is called velocity. That is called static pressure, right?
Static pressure. Yeah.
Okay, but whatever the pressure is here, you have to move towards the discharge, air outlet, right? So you require velocity pressure to move the duct, to move the air from one place to another place, right?
Yes.
So that is called velocity pressure. So you have a static pressure and you have a velocity pressure. So the static pressure will be acting on the duct surface. It will be this portion or this portion, but velocity pressure will be acting on the airflow path direction.
Basically, the airflow path.
So that is why you'll be adding static pressure plus velocity pressure to get the total static pressure, right? Total pressure. What is required for the fan to rotate. Okay, so if you go to down, that's the equations. There are Bernoulli's equation for the basic equation generation. Okay, and if you go further down, there is a head and pressure. Okay, the term head and pressure are often used interchangeably. However, the head is the height of the fluid column supported by fluid flow, while pressure in the nominal force per unit area. Okay, so this is the equation to calculate the head and pressure. Okay, so if you talk about static pressure, this is the equation P divided by rho g to calculate the static pressure. Okay, so P is the static pressure which we have seen. Say for example, 0.5 Pascal per meter or 0.6 Pascal per meter. That equation, that is the P is the static pressure. Okay, so velocity pressure, what is the equation? You can see the PV, velocity pressure, is nothing but density V square by 2, right? So the rho is nothing but density of the air, which is 1.204 kg per meter cube. Okay, by this equation you can able to summarize like PV equal to 0.602 V square, right?
Yeah.
Okay, so if you go, this is the equation, static pressure plus velocity pressure. Okay, so normally the static pressure, okay, it will be for the duct. The pressure will be acting on the duct. Okay, so that is the static pressure, and velocity pressure for the movement. So when you have a movement where there is a restriction, okay, when you have a velocity pressure, when you have a airflow movement where you will have a restriction, when you have a elbow or when you have a dampers,
when you have a bend, when you have when you're crossing through attenuators, when you're crossing through louvers.
Yes, clear, right? Okay, so that is the velocity, that velocity pressure you are going to calculate. Okay, so by using that equation you can able to calculate. Okay, now you might have seen that the manometer example. Okay, to get the value, what is the pressure drop, right, for the straight duct. So this value will be you can measure it in Pascal, the difference between the fluid level, right? You can measure the Pascal. Okay, so this is the laboratory test that when you do the laboratory test. Okay, so when you go down, the standard equation calculation as per ASHRAE. Okay, so you can see that pressure drop calculation. Say for example, I think you heard about this Darcy Based with
That's the
equation.
equation. That's
Okay.
4FLV square by 2G. I'm not sure that's the equation, but I
Yeah. So
think
yeah,
so.
this is the equation. This is the equation to calculate your friction losses in terms of total pressure. 1000 FL divided by DH rho V square, right?
Yeah.
By 2.
By
Okay. So this is the equation. Okay, for to calculate the static pressure, right? Okay. Now you can able to see that duct roughness factor. Okay, depends upon the different duct material. Okay, you may use carbon steel. Sometimes you may use galvanized steel. You may use longitudinal seams, right? So it depends upon the different factor. You have a absolute roughness value.
Okay.
Okay. So
Yeah.
how you calculate this friction factor? This friction factor is based on the roughness. You can see the roughness here. Okay, and based on the Reynolds number. Okay, so the Reynolds number, I think, if you go, there are different velocity having a different different Reynolds number. Okay, to calculate the Reynolds number, you can see the formula here: dV divided by 1000. Okay, 1000 V. So d is nothing but diameter, velocity, then 1000 divided by 1000 into kinematic viscosity. Depends upon the fluid viscosity, right? So that is why you can calculate Reynolds number. Then if you go to Coolbrook's formula, the graph, you can able to calculate directly from the Reynolds number and type of material, you can able to calculate the friction drop, friction factor.
Okay.
Okay, that also I can explain you in future based on the Coolbrook equation or say for this is the equation basically. Okay, you can say Coolbrook's equation 1 by square root of friction factor equal minus 2 log E is nothing but absolute roughness divided by 3.7. D is the diameter plus 2.51 divided by Reynolds number multiplied by square root of F, right? So here also you can do 1 by F is nothing but this F you can put minus 2, right? F power minus 2.
Yes, F power minus 2. Yes, yes.
Okay, so by this equation you can able to solve this value to get the friction factor. Okay. Okay, that is one method. Other method, if you go to there is a chart available. Okay, for Coolbrook chart available. So you can directly go to that chart based on the airflow rate and based on the material roughness. Okay, you can able to calculate your friction factor directly based on the Reynolds number.
Okay.
Clear, right? That I will show you in future. I will show you how to calculate the friction factor. But I'm giving you some idea. Okay.
But can I ask you something, Barney? So can you tell me what are the applications that we actually use this in, like in design? Do we use this much or
No, I didn't get you.
no? From a design point of view, say when we are working on projects, have you come across a scenario where we have to use these or?
Okay. Actually, it is not required to use this one. Okay. Say for example,
Okay.
this just to get some idea. Okay. Basically,
Okay, where the origin is from for
yeah,
the
originally it is coming from. See, now if you go to this is the ASHRAE duct fitting base. I think hope you have this one, right?
I don't have the software. No.
Okay. So this is the software. I think I can share it today. You can able to install in your PC. Okay. This is the software duct fitting base. Say for example, if I go to rectangular duct, straight duct. Okay. Say for example, if I have a 300 by 300 duct size. Okay. And this is the absolute roughness. Can you see that absolute roughness here?
Yes.
So based on that, it will calculate the friction factor. You no need to calculate basically. You have a software.
Okay,
as of now, as of now, nothing to require to calculate. No, you do not require to spend time to do some small equations, right? This is available in the calculator, and even if you do that research, it's not going to help in your career. Okay, so I'm just giving you some idea how you got this friction factor. So you have a readily available here. So this based on this absolute value, this friction factor all will change. The Pascal.
So we will have to add the variables such as the absolute roughness and the flow
absolute roughness. What is the velocity and what is the airflow rate and what is the length? Okay, this is a per meter length. Then if you calculate, it will give you the Pascal, which is 2.2, right? Okay. So this is for the straight duct. So straight duct, what is that? Only static pressure, right?
Yes. Only static pressure. Yes.
Okay. If you go further down, the standard method to do the calculation. Okay. This is the graph. Say for example, in this graph, you can able to get directly the friction loss per meter based on the airflow rate. This particular chart is created based on different equations, right? Okay. So we are not going to do that equations. Okay. Say for example, this is the for round duct. Okay. Well, the density is given here based on this density and based on this roughness. They have given the chart. So You can simply go to this particular chart, go to the flow rate, okay, and what is the diameter of the duct. You can able to get the friction, or you can able to get the velocity. So this everything is available here. We no need to calculate. The graph is available, and even you have a calculator. ASHRAE software is available. You can calculate your duct velocity, what is the velocity, and what is the size. Everything we can get it, right? Okay. If you go further down, okay, so here you can see the velocity. What is the typical design velocities for HVAC component, for louver, for exhaust, okay, for the filters, everything is given here. Okay, here you can see that the duct design methods. There are different design method, equal friction method, static regain method, okay, T method, optimization, right?
Yes.
Okay, you can see one of the picture where you have a duct routing. This is the motor or blower, and this is the routing, and you are going to calculate the static pressure, right?
Can I ask you something, Pranny?
Yeah, tell me, yes.
So you said we've got like the absolute roughness factor, which we use for different types of ductwork material and everything. Correct?
Yeah.
So my question now is generally for projects. Say we use carbon steel or
We use normal GI, galvanized ion, right?
galvanized iron. Okay. No, I wanted to confirm. I wanted to confirm because I
Yeah,
just saw only
galvanized
because
ion.
I didn't see the galvanized iron
No, you have a
exactly.
different, you have a different materials and different roughness factor.
Yes.
So what type of material we are using, we can able to apply that roughness factor.
But typically, as of now, in projects, we use more like galvanized iron.
Galvanized ion,
Ductwork.
GA duct work only. Every
GA
project GA duct work. Okay.
Yeah.
For,
Okay.
because when you cannot use plastic material because the pressure is very high and the plastic may get damaged.
Yeah. Plastic. Yes.
Okay, so that is why we are using.
Even this is the case for the smoke exhaust ductwork, smoke makeup ductwork as well.
Yeah, smoke ducting also we are using GA duct only, but it will be with the fire rated material.
Will be fire rated material. That's it. Okay. Understood.
Yeah. Okay. Now you can see the standard calculation method, total pressure loss calculation by using this standard as per ASHRAE. Okay. So can you see that duct fitting one fitting numbers? You have a duct, you have duct fittings, right? Then you have airflow rate. This airflow rate can be anything based on your drawing. And what is the duct size? 300 diameter. Okay. This velocity 9.9 Pascal. So how to calculate velocity? I'm talking about if you go to calculator, you will get everything here standard, right?
Yes.
See, this is the, can you see this particular, when I open the software, directly it will open here, right? The CR11 fittings. Okay. See, everything, whatever is given here, if I go to round duct, okay, straight duct, can you see here? If I click straight duct, it is as per ASHRAE, 300 diameter. Okay, this is just for an example for us to understand. Okay, 300 diameter. Okay, and this is the roughness factor 0.09 for the duct material, and the flow rate is 700 liter per second. Densities of the air will be 1.204. You can able to calculate velocity, right? Q equal to pi by 4 d square multiplied by velocity. So velocity is nothing but Q divided by area. So you know the area, you know the what is the diameter. So based on that, you can able to calculate velocity, right?
Your velocity. Yeah.
Okay, and the velocity pressure formula, you know.
Yeah, that is PV equal to 6 points. That's the equation, right?
That is the equation. So by using that equation, you can able to calculate velocity pressure, right?
Velocity. Yeah.
And also the friction factor. Also, you know the equation how it came from.
Yeah, we using Darcy's equation, right?
No, friction factor is using Coolbrooke.
Coolbrooke.
Yeah, and the pressure loss calculation is based on Darcy equation. Okay. So this is the way you are getting. See why I am explaining this much. Okay, say for example, somebody maybe you will go to somewhere. Okay, somebody will ask you to just open the software and use that sizing. You cannot. You don't know the what is the basics, right?
The basics behind it. Yes.
So this is the basic as per duct charter. Okay. So you can able to calculate your duct velocity based on equal friction method, right? Okay. Then if I go to any of the fittings, say for example, this is the fittings elbow. Okay. Okay, example, you have a different type of elbows, different type of fittings, dampers. Okay, I think you can see, right? Different
Hmm.
type of dampers, elbow. Then you have a obstructions. Okay, screens. There are
Hmm.
different fittings, dampers. Okay, then you can say there are sometime you will have a sound attenuator as well.
Hmm. 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 Hmm, hmm. No, I understand where you're coming from. Yeah, yeah, yeah.
Okay, so all the fittings, how to calculate? There is a same. You can use this different fittings, right? You can use that different this one. Okay. Now, how to calculate as per manual? Okay. To use your software is very simple. You will go to that particular sample here, and you will fill the data, and you will get the pressure drop, right?
Hmm. Hmm. Hmm,
You
hmm,
can
hmm.
able to see
Understood.
now. You did not use this software before, right?
No, I have not. I have not.
Yeah, you can able to go to transition piece. Say for example, this is one of the transition piece, right? There is a duct
Okay.
reducer. Okay, so you have
Yeah.
to give the airflow rate, height, width. What is the design based on your design? Based on the duct
Hmm.
equal friction method, you can able to size the ducting.
Yeah. Yeah. Yeah.
Okay, and
Hmm.
you can
Hmm.
provide the length. Okay, then you can provide the flow rate. Okay,
Hmm. Hmm.
and
Hmm, hmm.
it will calculate angle, everything based on the standard. What is the angle? Everything.
Hmm. Hmm, 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 hmm,
This
hmm.
itself it will calculate, and based on that, it will give you what is the pressure drop for this particular fitting, 20 Pascal.
Okay. After considering variables such as your duct sizes and your flow rates, basically,
Yeah.
and the rest is getting calculated, and you can get your pressure loss from there. Understood.
Yes. Yes. Okay. Now, if you go to manual method, okay, just for you to understand for the fittings, say for example, you have a 700 liter per second, velocity is there, then there is a velocity pressure, okay, and this is the fitting loss coefficient,
Hmm.
okay. So the fitting loss coefficient multiplied by velocity pressure is nothing but total pressure.
Your actual total pressure. Hmm.
Okay. Say for example, 59 multiplied by 0.32. Okay. 18.88, which is nothing but 19.
19.
Okay. So how to get this fitting loss? Okay. You can able to get this fitting loss from this software, right? You
Yeah.
can able
Fitting
to get the
loss. Fitting.
loss coefficient. Loss coefficient is
Yeah.
given
Loss.
here.
Hmm. Hmm.
Okay.
Hmm, 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 hmm.
Clear, right? Okay. So from there also
Yeah. Yeah.
you can able to get this value.
Understood.
Okay.
Understood.
And if you want to
But
get the value,
is there another table? I don't know if I remember because
yes,
in
yes, yes, it
ASHRAE
is
itself
here. It is here. It is here.
there
That is what I'm
is.
going. Okay. See, for
Okay.
example, here,
Understood. Yeah. 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 I've seen this.
this
Yes.
is
Yes.
the
Yes.
this is the fitting loss coefficient for the elbow based on the diameter, based on the angle.
Yeah. Yeah.
Okay. Say for example, this is
But
the
then
diameter.
these are, but these angles are more like C0. Oh yeah, understood, understood. Yes, yes, 90
Okay.
degree
But
bend. Yes.
you don't need to use this one.
Mm-hmm.
This is just for you to
Because everything
understand.
is covered in the duct fitting database basically, and
Database
then
here. You will get directly the value here, 1.39.
mm,
And based on this
mm,
1.39, it will calculating your pressure directly.
understood. Yeah.
Okay. If you want to cross check, we can do the cross check here. This is the 15 is the velocity pressure. Okay.
Yeah. Yeah.
And your loss coefficient is 1.39. Let me check. 15 multiplied by 1.39 is nothing but 20.85. Okay.
85.
Maybe this particular 15 is not actually 15. Maybe it is something 14 point.
14
Uh,
point something.
some
Yeah, yeah,
some some value will be there. That is why based
yeah.
on that
They've just
they have
rounded off
calculated
to the closest
20.
integer, and then they just goes to
Yeah,
yeah, yeah.
20 Pascal.
Understood.
So, but basically this is the equation. Clear, right? Okay, so
Yeah,
here
yeah,
you will
understood.
get loss coefficient. This loss coefficient you don't require to calculate here by using this one. You have a software
Yeah,
to get the loss coefficient. Okay,
that's good.
but here it is very simple to get the loss coefficient. What is the value here? They have explained. Say for example, this is the elbow, right? This type of elbow you can
Yeah,
able to calculate. See the loss coefficient depends upon the duct sizing, duct
the duct
diameter.
sizes. Yes, yes, yes.
Okay, then you can
Yeah,
able to
understood.
get the value
Mm,
here. Okay, then if
mm,
you go
mm.
to this one, this is a C value, this is a C value based on the N. N is nothing but free area of the screen,
Yeah.
like 30%, 50%, okay,
Mm, mm,
70%, 80%, that based on the free area and based on the area A1 by A0. This is the A1, this is the A0.
mm.
So based on that, you can able to get the coefficient value. Okay, but this just to get idea, you no need to go in detail.
No, no, understood, understood. Yes,
Because you
yes.
have a software. This software I will be sharing with you. You can able to use
Yeah.
the software for you can check, you can do the calculation itself. Okay, very simple.
Okay.
There is an Excel sheet as well. I'll be sharing with you. uh, Let me open the Excel sheet.
Yeah.
These are calculation sheets. Okay, you have a same supply
Mhm.
fan, velocity,
The
volume,
same manual thing which you
same
have
thing,
done is basically in an Excel format. Okay.
same format. Velocity pressure you are going to calculate. Static pressure you are going to calculate by using Darcy Weisbach formula. Velocity pressure,
Mm.
loss coefficient
Based on
from the
yeah, yeah.
chart, either from the chart or from the calculator. Friction factor also either from the chart, right?
Yeah, yeah.
Okay, then the velocity you can able to calculate area, length, whatever you can calculate. Then there is a pressure drop. Okay, then for
Yeah.
the
This
grill,
friction factor is basically is that the E or is that the coefficient of friction?
no, no, it's not a E. So from the E, based on the E, and based on that you have
Yeah,
to
the F,
calculate the
right?
friction.
F is the friction factor. Sorry, my mistake. F is the friction
F
factor
is the
and
friction factor.
understood, understood. Sorry, my mistake. I understood. Yes.
Friction factor is different, loss coefficient different.
Yeah, what we saw was loss coefficient on the other side. What we've seen right now is the friction factor.
Yeah, friction factor. Yes. To calculate friction factor, there is an equation, right? Yes.
Yes, yes, yes.
Okay,
So
but
in that the other the no the loss correction loss doesn't come under that, right? That is only for uh as the correction no the correction doesn't come in this one though, right? No
which correction?
correction factor. The correction factor that is can you go back to the Excel sheet, please? After the friction factor, you had another column that is only for bends and everything,
Loss
right?
coefficient. Loss coefficient.
Loss coefficient. Loss
This is
coefficient are
only
only
for
for
elbow or
bends.
fittings, elbow or bends and pressure bends or VCD damper, something like that.
Understood.
Okay, and for grill, louver, sound attenuator, you can get the pressure drop directly from the manufacturer data.
Understood.
Okay, so clear, right? So you can able to
Yeah.
calculate your total pressure. Then after that, you can take 10% safety factor if required. Then this is the total
Yeah.
static pressure calculation for the ducting. Okay, so basically
Mhm.
this is the equation for the velocity pressure. This is the equation for static pressure. Okay, and I have attached
Mhm.
one video to understand what is static pressure, what is velocity pressure. Also, you can go through and uh, you have a design criteria. Okay, there are different types of duct designing methods. One is equal friction method, velocity reduction method, and static regain method, right? And
Yeah.
if you
Yeah.
talk about, there are three different applications. Okay, you have a three types. You have a three different application. Okay,
Yeah.
and
Yeah.
based on that, you can able to size the your duct
When
sizing.
you mean three different applications, you mean to say the different pressure per Pascal per meter values, right? That is what you're trying to say, right?
Yeah, no, what I'm saying, the equal friction method, you have a one method, and a
Yes.
static method is one
There's
method.
static method. There's one method.
Velocity
Okay.
reduction method is one method. Okay,
One method. Understood. Understood.
you
Yes.
can use that three different applications. Okay, so this is
Mm-hmm.
the way to calculate your total static pressure. You're clear?
Understood. Yes. Yeah. Yeah.